Okay, we moved on to chapter 9 now, and we're talking about periodic properties. So, if you remember with quantum mechanics, when L equals 0, we have an s orbital, L equals 1, we have a p orbital, L equals 2, d, L equals 3, f. And we're going to start with the first electron in the hydrogen atom. So, one electron in the 1s orbital, this is 1s1, so that means one electron in the 1s orbital. And the quantum numbers are going to be n equals 1, a equals 0, m sub l equals 0, and the spin plus or minus 1 half. Now we're going to add a second electron with the helium, the ground state of helium, two electrons in the 1s orbital. We have this 1s squared. That means two electrons in the orbital, and it is paired up like shown there. And you have two electrons here, and the difference is that one spin is plus 1 half, one spin is minus 1 half. And these electrons are really in the same space at the same time. Their magnetic fields are just opposite of each other at any given time. And then we have the Pauli exclusion principle we talked about before, that no two sets of fermions within the same atom can have the same quantum numbers. And also for hydrogen, though, well, I mentioned this Pauli exclusion principle that before. This gives yields to reason why atoms have structure, and I'm gonna hear that. That's my hand trying to go through the desk that I have my computer set on as I'm recording this video, and you can obviously hear the bang on it. What is that bang coming from? The electrons in my hand are touching. Well, the fields are interacting with the electrons on the desk, and because of the Pauli exclusion principle, there is a pushback. So that's also sometimes referred to as electron degeneracy. That's what keeps stars together, for instance. And it's pushing back, and that's the reason why I can't put my hand through the desk, and it pushes back with a normal force if you go by physics. Can you overcome this electron degeneracy? Yes, you can. In a neutron star, there's enough gravity that the electrons can be pulled into protons to make neutrons, and then you have a neutron star. So there is a limit, like I said, to that, but it has to deal with an extreme amount of force for very, very heavy or very massive stars, at least 3 times the mass of the sun. But okay, moving on. Let's talk about for hydrogen atoms. So a hydrogen atom or hydrogen-like atom mean only one electron. All of like the same set of quantum numbers. So n equals 3, 3s, 3p, 3d. These are all the same energy, also known as degenerate. So when there's more than one electron, the electronic field and magnetic field affect the energy levels. The electronic field interacting with electron energy levels is called the Stark effect, and the magnetic field interacting is called the Zeeman effect. So for the energy levels in electron, the Zeeman effect is more pronounced. In Coulomb's law, the electronic field is 1 over 4 pi epsilon naught, charge of 1, charge of second over the distance between the two charges, and the force is 1 over the distance squared. So those are the Coulomb's law there. And that is the effect of the charge, and that's what binds the atom together. Among other things. They all these things as structure, the Pauli exclusion principle structure, but then the negative electron is attracted to the positive nucleus. And the closer the electron is, the more strongly bound it is. As we've seen before, the lower number n's are closer to the nucleus of the atom, and those electrons are similarly harder to remove from it. And let's talk about shielding and penetration. So here is a lithium atom. So you see here you have the lithium atom. You have 3 electrons, and there's 2 electrons in the inside. Those 2 electrons, so lithium's outer electron is shielded by the 2 inner electrons. That means that the charge is about plus 1. But the 2s orbital has a a little bit of density closer to the nucleus, and then that's the penetration of that. So it feels the charge a little bit. That feels the full +3 charge of that. So that can affect the wave function. Okay, let's move on and let's talk about the building up. This is called the Aufbau principle, the building up principle of electrons. So if you have one electron, it's just like that. Let me make my pen darker. So this is hydrogen, this is helium, here's lithium, here's beryllium. Okay, so now we go to boron. Boron, it goes up to the 2p, and I'm just going across the periodic table if you want to know these numbers. The next electron would be carbon. Where does carbon go? Does carbon pair up here, or does it go here? It goes here like that. It goes into its adjacent orbital, and this is known as Hund's rule. And then the next one, nitrogen, goes up like that, then oxygen, then fluorine, then neon. So for Hund's rule, I like to swim, and when you're swimming laps, it's really nice when you can have your own lane. That's kind of nice. Sometimes, though, if you have to split a lane, you have two swimmers, and I always have to like keep my eyes open to make sure I don't bump into the other swimmer. That's kind of like this situation here with two electrons. You know, it's cool that they can share the orbital, but they would rather be alone. So that's Hund's rule. So okay, so we're back up to neon. So there's neon. Here is sodium again, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, and so on. So this is the way the electron builds up. It builds up that way, using electrons and populating that way. And this is the same thing that you see here. So this diagram here, we're building up, and the thing to note is that we have parallel spins in this place. You could have this situation, the electron goes in that. That would be an excited state, though. It can happen. That's an excited electronic state, though. So let's see if you're following. What is the ground electronic configuration for sodium? And this one is wrong because you don't have that many electrons in the 3s orbital. So you can only have 6 in the p orbital there. So we're choosing between B and D. B is the right answer. D is possible, but it's an excited state. So this is the ground state, so the lowest energy state. Okay, and I'm going to move on. I've talked about this a little bit. Valence electrons and core electrons. So valence electrons are outer electrons, core electrons are inner electrons. So I kind of think of this in terms of like clothing. So hydrogen having one electron, this is akin to someone wearing a one-piece bathing suit. So this person has a one-piece bathing suit on, and he or she is wearing no other clothing. And helium is sort of akin to someone wearing like a two-piece bathing suit. Something like a bikini. So you have a top and a bottom and nothing else. So just 2 items of clothing. So then lithium is like someone wearing a trench coat with a 2-piece bikini underneath that. So someone's wearing a bikini, and then you have a trench coat over it. The trench coat is covering the clothing underneath. So valence electrons, these are like clothing that you wear on the outside, and the core are like underwear, clothing on the inside that you, in theory, should not be able to see and don't interact with the outside world. So just like that, and you keep on building up, and more clothing is added on, more and more electrons are added on. So, and listed here, these are the electron dot structures. So it's the Lewis theory. We'll talk about it more next chapter, but these are the Lewis theory is showing as electron dots. But that's the difference between core and valence. Core is inner electrons, valence are outer electrons. And one of the reasons why we organize a periodic table the way we do is because of the same valence electronic structure. So along a column, each each set of elements has the same electronic structure, or similar in most cases, very similar, at least same valence electron structure. So let us look at the electron configuration for germanium. So writing out the electron configuration for germanium and using the periodic table. So here is germanium right here. And what is germanium? It's going to be 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d10, 4p2. Okay, and then I'm getting this in the periodic table. This is the 1s, here's the 2s, 2p, 3s, 3p, 4s, 3d, 4p1, 4p2. That's where you find it. And a shortcut is this right here is the electronic configuration for argon. So you can write this as argon 4s2, 3d10, 4p2. And the valence are the highest n. So identify the valence electrons. I'll use yellow. Here are the valence electrons. Those are the highest n only. The valence electrons are the 4s and 4p. So germanium has 4 valence electrons. Okay? And as I stated before, this is where how you use the periodic table. And I can go on, and here's another example for selenium. So selenium is right here on the periodic table, and you can write it using argon's configuration. Germanium's just right here. So it's the same thing as germanium, but it's 4p4 instead of 4p2. So, and this is how we organize periodic tables due to this orbitals. Okay, so on to the next section.